Our speaker for today's lecture, Mr. Vinod Jangid sir, is here with us. He's the director and CEO of SSTPL, and he has 19 years of vast experience. So, without wasting much time, I request the honorable speaker, Vinod sir, to please start the lecture. Vinod sir, over to you.
Yeah, thanks. Thanks, here. So, with this, I welcome all the participants from the side of SSTPL. We welcome you for this session where we will be talking about IoT and LoRaWAN. We at SSTPL are working towards simplifying large and complex IoT. What means of large and complex IoT? Large government infrastructure, large public infrastructure, large industrial IoT ecosystem. So SSTPL works towards that particular ecosystem. So we'll discuss few about IoT, then we will move to LoRaWAN. So IoT is very important. Why? It is because it is having a large ecosystem developing day by day, as well as it is making things simpler. So if we look at the market size of IoT, it is growing day by day. So next slide says about that, where we are and how we are going. So see, in 2010 to 2020, where we have been grown, we are expecting a trillion of TB data going together here and out in these devices. So look at these numbers: exponential growth month on month, year and year. 30.9 billion devices working on IoT by 2025. It's a big opportunity. So whole of the world is looking how they can leverage out from this opportunity. If you look further, the scope of IoT. So IoT is there in transport logistics. We all are aware of the vehicle tracking systems, which is one of the first use cases of IoT, where you have the complete information about the vehicle movement. You also have information halt. We also have information related to fuel. All things can be tracked through IoT. Goods tracking, another important opportunity coming up these days, where you have some very precious items or maybe perishable items. Tracking those goods is very important. So we have analytics, we have the software stacks coming up from different ecosystem partners to build this application generously. Utilities, again, a big use case for IoT. Smart metering, you all must be aware of that. Energy meter has been there on the AMR ecosystem since long. But efficiency is yet to be begun. With the IoT, we feel that there should be some 99% of accuracy, 100% accuracy coming up on smart metering. Smart grid, again, is a part of power distribution, power generation, and power transportation ecosystem, where power failures, grid failures can be avoided through IoT. IoT devices connected with grid tell us where the load shedding is required, where is the there is a excessive load is drawing with someone, or which needs to be upgraded, which transformer need to be replaced, which house is required to upgrade their load permissions. So smart grid helps in many ways to industries, to domestic consumers, to government. So that's how it is. Smart building, we have seen multiple devices coming in, different use cases in smart building, from sensor, fire, from lighting, some Alexa coming in, Google Home is coming in. All those are, use cases you already have aware of that. Wearables, wearables for consumers. Wearables gives us information about your basic bio sensor data. They also tells about the movement of your loved ones. Wearables also saves lives by tracking the people in the most hazardous places like mines, some petrochemical plants. Going further, the industrial IoT. People talk about Industry 4.0. Industry 4.0 is bringing together the IoT sensor ecosystem, the application ecosystem, and the production efficiency. If we put it together, Industry 4.0 makes a big use case for coming years, or at least 10 years, we will see phenomenal growth in industry IoT system, where you monitoring the device, which is having sensor data, temperature, the rotational force. It can also predict the life cycle. It can also help in understanding how the upgrade is required for machinery. So this is huge ecosystem development happening. Environmental monitoring, environmental, we see, every day WHO talks about, issues related to environment. UNICEF, everyone is, concerned. There are, meetings has been happening since last 20 years to make improvement. But here, with sensors connected with IoT ecosystem can help where the immediate action is required, where you need not to wait an immediate act, maybe a water installation plant of Ganga, or maybe something happening over some forest area, or maybe some ecosystem where virus proliferation can be stopped. So there's much to do. So we shall look at coming years how environmental sensing and monitoring will be evolving. Agriculture is a big use case. India, or specifically our country, which is dominantly on agriculture, sensing the moisture level, sensing the chemical structure of soil, and suggesting farmers to have proper crop production. Also helps in irrigation. You can automate irrigation system based on the sensing ecosystem. IoT is day by day growing. Livestock tracking, another use case where you have a large field. Your cows are grazing around here and there. You need not to track them. You just have an IoT sensor engineer. Today also there are radio collars has been used, but they are not so efficient. With the IoT, you have some more data analysis happening out there. So this is the scope of IoT, which is growing further day by day. These are the some use cases. We have many more use cases which comes in the smart city and government ecosystem. So these are the key components of IoT. You all must be aware that devices are required to be smart enough to gather data, to analyze data, and to send it to their required network. Network is again a big challenge for IoT ecosystem. Till date, we have been mostly rely on 2G data. These days, we also have 4G, but network connectivity remains a big challenge in terms of Wi-Fi, in terms of PLE. Still, we can gather data from nearby places, but when we talk about far-reaching places, it's a big issue till now. Telcos predominantly are more focused on their revenue customers, high revenue customers coming from voice and high speed data. They're not very much concerned about IoT and small devices. So this is another opportunity as well as component of IoT. Platform applications. This is one of the most important, one of the most valuable ecosystem where the companies like IBM, TCS, Wipro, everybody is working on. They have their data centers, they have their and IoT engines, they have their IT stack to serve these millions and billions of devices. The system is every day evolving. You see IBM Watson, you would think that how easy to configure devices out there. So the components have been evolving every day. So I'll give for further more detail about these components. So like you see the device because device is the like smart meter or water meter or something like so this is how the device you can configure maybe any machine, maybe any clock system, maybe some traffic light system. So looking further, you have sensors, actuators, which are connecting with the devices to automate them, to give them the analytical data to work upon. So the sensors and actuators comes in. So you can have an irrigation system, will have a solenoid. So one irrigation system is a device, and then the sensor, the actuator, the solenoid will be automate them. And the third part of the hardware comes in the SIMs, eSIMs, the MCUs, the chip, the RF chipsets, all these which are connecting you to a network. Network means here is IoT network or data network. Connectivity, you have many options as on date. Cellular is one of the predominant market share as of now. But gradually we see LoRa is coming up. Wi-Fi is already there for home automation. PL is already there for tracking. Satellite is not very numbers, but we will see that when the large global players are coming in this, it will see growth. And the remaining is the backend, where you have the databases, you have the application environment, you have device management softwares, you have network management softwares, then we have the billing support, and then going further the integration with your customer applications. So, so predominantly IoT works with wireless technologies. Though there are some connected IoT technologies also, but predominantly it is on wireless. And if I categorize them, you can categorize in three main categories: short range, medium range, and long range. You see that you are aware of RFID NFC. So already they are in tracking, security, gate security, gate pass, vehicle movement. You're already using all these technologies. But day by day, RFID has been evolving. We see that RFID is in different bands is also available. NFC has been used, very contactless transfer, where you have to ensure that the user and the device are nearby, so that there is no false processing is happening. Medium range Wi-Fi, everybody know. Zigbee is another example of ISM band network, similar to Wi-Fi with a different architecture. Then there comes the long range networks, where the LoRaWAN, NB-IoT, and 4G LTE falls in. Now here we want to emphasize that 4G LTE is already available across India, across the globe, and they're serving millions of devices already. Now the coming up is the LoRaWAN and NB-IoT. They are catching up very fast. NB-IoT is a licensed band LPWAN, and LoRaWAN is open standard LPWAN. So there is a major difference between LoRaWAN and NB-IoT. 4G LTE remains high-speed data network. The comparison is like this: like RFID has a very less coverage area, a very less data rate as well. If you go to the mid segment, we have a Wi-Fi, which is having the largest data rate, Bluetooth, and then BLE. BLE is a Bluetooth with a low energy stack. It has lesser data rate, the packet sizing, and the channel selection is different from all existing Bluetooth ecosystem. And it also works in a very low power domain. Zigbee is not in a low power domain, such a low power domain, but still it has a low power than the Wi-Fi. The speed is also less than the Wi-Fi. The third one comes with the little longer range. Wi-Fi Hello is there, but it has not gained momentum till now. They're still fighting for some use cases. Cellular, you all aware. Then the licensed LPWAN. LPWAN means low power wide area network. So everybody I will repeat it, a low power wide area network. So this network, goes to the range of 1 kilometer and beyond. So LTE-M, NB-IoT comes in. Then we have the unlicensed LPWAN. If you compare with licensed and unlicensed band, there is a data rate difference. But unlicensed LPWAN has a bigger, range of areas. If we compare that, the coming slides.
In today's business world, accessing real-time data from key assets is a critical need. Companies that collect and act on real-time data operate more efficiently and improve their bottom line. As digital transformation accelerates, companies cannot afford to stay on the sidelines. Where to begin? LoRaWAN provides a simple way to connect and monitor your assets, unlocking the insights your business needs to compete. LoRaWAN is an open, global standard for wireless communications that businesses to use to get real-time data from objects out in the world and track asset locations in ways never thought possible due to high costs and technical barriers. Using LoRaWAN connected sensors, any company can easily obtain the insights they need to automate processes and improve efficiencies, increasing the bottom line and even creating new revenue streams and business opportunities. The LoRaWAN standard was created by the LoRa Alliance, a global association whose members' ecosystem develops and manages the LoRaWAN protocol. LoRaWAN was specifically developed for large-scale IoT communication, such as the need to cover vast distances, to transmit signals through physical barriers, to run on low power and ensure a long battery life, and massively scale at low deployment and operating costs. LoRaWAN improves health, safety, and welfare for all citizens, while also improving businesses' bottom lines. Utility providers who use LoRaWAN save resources, reduce costs, and improve services for themselves and their customers. It makes cities smarter, safer, and cleaner. It streamlines logistical operations and asset management, increases yields and conserves natural resources, and even prevents accidents, improves patient outcomes, and saves lives. The benefits of LoRaWAN are many. LoRaWAN has the most public and private network deployments of all LPWANs globally, which provides coverage worldwide. It penetrates barriers that block network communication, reaching devices underground, through concrete, and at high elevations. LoRaWAN has a very long range. It communicates with objects up to 16 kilometers away with a clean line of sight, and up to 5 kilometers in dense urban environments. LoRaWAN is also very robust. It operates without issues in harsh weather conditions and noisy communication environments. LoRaWAN is incredibly power efficient, using very little energy when communicating with objects. Sensors can be installed in difficult-to-reach locations, and the battery can run for 10 to 15 years without being changed. LoRaWAN also delivers firmware updates over the air, so you don't need to send a technician to update devices. This slashes maintenance costs and improves long-term agility. LoRaWAN is unique in its flexibility to accommodate different business models, such as CapEx and OpEx, and the ability to choose public or private networks to meet your security and operational needs for all industries. A smart city that requires its own private network. A farmer who prefers to join a public one. A multi-location company that wants to tap both private and public networks. LoRaWAN is uniquely suited to meet diverse IoT needs. LoRaWAN.
So LoRaWAN is a low power LPWAN network which has been developed by two engineers in France. And it has been now taken over by Semtech. So Semtech is the LoRa technology owner. The patent is with Semtech. And LoRa Alliance is a global alliance which is working for standardization of LoRaWAN protocols. So whomsoever developing a product on LoRaWAN, should comply with the LoRaWAN specifications. So we have specifications from regional specs. There are different specifications for each country and each region. India have a different ISM 865 to 867 megahertz band. So our specs are different from that spec of some country in China. You say about Indonesia or maybe Malaysia. Every country has their own LoRaWAN stack. So LoRa Alliance is a global body which takes care of all these specifications. And the people who are the part of the alliance takes care that the specifications are being followed. Globally, more than 600 companies are part of this. They are developing the product which is ranging from end node to gateway to LoRa network servers. So this is how the ecosystem works. We already have this discussion in video just replayed, but still I am again coming to the points related to LoRaWAN. LoRaWAN has a long-range IoT network, which is it makes it very different from other IoT networks which has been used till late. People use IoT network in terms of Wi-Fi and BLE mostly. Nowadays, LoRaWAN, taking space of those particular sensors and devices which do not need much, data rate, but they need a longer range. Like we talk about agriculture sensors. So the vast land of agriculture, you can put a moisture sensor, which can tell us about when you need to have, water supply for the particular farm. This sensor can be, some 10 kilometer away or maybe 15 kilometer away. If you are putting on gateway on some, decent height, you can achieve this particular length we are talking about, 15 to 20 kilometers. Even in the urban dense areas, you can even achieve 3 kilometer kind of range. Now, this 3 kilometer range is not in line of sight. It can be in a deep, it can be in, some mall or some, lift, some staircase or some shaft. LoRaWAN can penetrate those locations as well. Top of this, LoRaWAN works with a very low power. LoRaWAN has architecture. It goes in sleep. It comes in. It just wakes up, sends the data, and goes back in the sleep. By doing this, all activities, we can achieve a very long battery life, maybe 10 years if we have a very low data packet sending every day. Maybe one packet every day we are sending for let's say 10 bytes or maybe 20 bytes. You can achieve this 10 years of battery life. Security, we just discussed with AES 128-bit encryption end-to-end from gateway to server also. The payload when has been picked up is been encrypted in the device itself and it decrypted on the server side only where you have the TLS encryption is also implemented. Standardization, we discussed the alliance is doing this. So there is interoperability between devices. Devices you buy from any one of the manufacturer in India will comply with each other. Network also, you can join this network. You can go to the other network. It will still remain interoperable. LoRa also offers a geolocation service without GPS module. Like you need not to have a GPS IC. LoRaWAN uses their own geolocation technology to give you a specifically 10 to 20 meter kind of accuracy in open spaces. So this is a very low cost GPS option. Wi-Fi is not, you say that mobile friendly device, you need to be 100 meter. Whereas the LoRa, when if you are putting gateway in a city, in a town, you can, roam around the complete town. So it's like you are having, cellular connectivity. So the mobility has been enhanced by LoRaWAN. High capacity is means with how many nodes can be connected with one gateway. We see that LoRaWAN has, different kind of modulation technology. We will discuss it later. With the help of this modulation technology, you can, connect, thousands of devices with one gateway. So it's a large capacity. Whereas if you talk about Wi-Fi or something, you have a limited number of channels. Maybe 15 devices, 16 devices can connect with one standard Wi-Fi hotspot. So we have high capacity as well. Cost is also low because You have a power cost is less. You have a battery which is running for long. You have a small device which can go through kilometers, so less number of gateways is required. The device cost in terms of hardware is also very less compared to other cellular network cost. So cost is also less. So it makes LoRaWAN, the one of the most advanced IoT technology and going like anything. This is the typical architecture. These are the LoRaWAN end nodes, connected sensor. We say LP1 sensors. They are connecting to the gateway. It's a star network. So it's a one-to-one, point-to-point protocol with gateway. The gateway communicates further with the LoRaWAN network server. LoRaWAN network server has backend with LoRa application servers. These application servers are having the device registration, device management, and furthermore integrity required for devices. LoRaWAN network server maintains connection with LoRaWAN gateways and sends the data over a period of interval. So there is a what is MAC command, MAC layer architecture, which controls all this. So this architecture has been shared between devices and networks. Here the gateway works as a transparent devices. Their main purpose is to have RF infrastructure ready. Here it takes the data on LoRa physical RF and send the data back to LoRa network server or an IP network. So you can have a backhaul of IP on a Wi-Fi, Ethernet, or cellular 4G. End-to-end protection is enabled to AES-128-bit encryption. We encrypt data here. From here onwards, you can send the data over a TLS or SSL or whatever security you want to need. So this is typical LoRaWAN architecture. Going further, we will have a discussion about the modulation. So what is different in LoRaWAN? LoRaWAN uses CSS, the chip spectrum. The technology is already used in some military radio systems since 1960, but it has not been used in civil architecture. So LoRaWAN is using that. So you can see that you have chips, up chips and down chips. So this changes the modulation altogether. It's very different from modulation of AM or FM or maybe FSK or something. So chips are changing every time. So it is changing in the frequency domain. It's also changing in the time domain. The resultant, if it is as you can see that. You see the different aspect factors are coming in. You see these chips are changing every time. And the resultant D chip symbols are like this. They are changing every time. This is another illustration where you see on the time domain, it is changing every time. So these are called as spreading factors. Different chips are called spreading factor from SF7 to SF7 typically. I have some more detail on this video.
A plain radio signal carries no information, apart from the fact that the transmitter's been left on. The signal has to be modified in some way to be used to convey information, and there are a number of ways in which this can be done. Two of the most popular methods are to modify the amplitude and the frequency, and these will be familiar from the fronts of the traditional radio, AM and FM, amplitude and frequency modulation. Listeners to AM radio will be aware that it's more susceptible to interference from natural and man-made sources because it's not as sophisticated as FM, which is clear and resilient, and is a more complex and unnatural waveform. AM and FM will be easily recognised because of their widespread use in broadcasting. Here, we're not concerned with music and speech, but just binary ones and zeros. Digital 1 and 0 signals could be sent using AM by just keying the signal on and off. Crude but effective. With FM, one frequency could be used to represent a 1 and the second for a 0. This is also a common method and called frequency shift keying, FSK. We can see this signal jumping between its two frequencies here and recorded below in what is called a waterfall display. FSK is important as it's simple to produce and detect and is referred to in LoRa radio transmissions. But LoRa goes further and in doing so becomes more complex and even more resilient to background noise. Rather than just use the two frequencies of FSK, it sweeps between the two like this, up and down. Now, there are two parameters that may be changed on both the rising and falling signals. These are the rate at which the sweep changes, call this the sweep rate, and the range over which the sweep could change, call this the bandwidth. There are always compromises in communications, and here there are compromises in both sweep rate and bandwidth. Increasing the bandwidth provides a better quality signal, but bandwidth is at a premium. Everybody is vying for space, and bandwidth is valued and restricted. Engineering involves maximizing performance using minimal resources. Bandwidths specified for LoRa are therefore restricted under international agreement to 500 kHz, 250 kHz, and 125 kHz, and in Europe further restricted to just 250 kHz and 125 kHz. A slow sweep rate is easy to decode and becomes progressively more difficult the faster the change. Here's another potential trade-off. The faster the sweep rate, the more information can be passed, but the more difficult it is to accurately resolve the signal. The European system uses 6 different sweep rates, or spreading factors as they're referred to. These are referenced by numbers 7 to 12. We've already seen that LoRa devices use a LoRa, which is a protocol where any device can just wake up and transmit, regardless of any other existing conversations. As an alert, a device will start by sending this unique training cycle of 8 up sweeps, followed by 2 down sweeps. We can break these sweeps into symbols of equal period. The block of 8 is called the preamble, and followed by 2 symbols used for timing, called the synchronizing symbols. Any listening device can clearly recognize this preamble as the beginning of a packet, which alerts its attention. The transmitting device is then time limited by which it must complete the rest of its transmission. All of the data content of the packet is contained in the following symbols. Each symbol contains a discrete frequency step representing 8 bits. The data contained in each sweep is probably best shown using these examples. The details, like all good comedy, is in the timing.
We learned about spreading factor. So LoRa is multiple applications coming out from spread factor. You can see a best signal occur. So this video tells about how signal and spreading factor and the data rate negotiate with each other. So this video tells about more of that.
The best signal occurs when the endpoint and the gateway are in close proximity, but as we've seen, the attenuation increases as the distance increases. Eventually, the power of the received signal becomes unusable. This could be likened to trying to hold a conversation at a greater and greater distance. Now consider the same situation as a noisy party. The temptation is to raise your voice, but little is achieved if everybody shouts at the party. Or, in radio terms, all this does is drain the battery even more rapidly. An option would be to speak more slowly and clearly. This is what LoRaWAN does, electronically, and it's called the spreading factor. As the distance increases, the signal is sent with the spreading factor stepping from 7 nearby to 12 at a distance. If every communication was just allowed to follow this pattern, the temptation would be for the whole network to slow down. To stop this situation from occurring, there's another rule that limits the total amount of time any transmission can take, and this is quite draconian, just 1% of the allowable time. Short-range communication speaking rapidly can therefore pass more data at the higher rate than the more language can do at distant extremes. This trade-off of distance against power transmitted and quantity of data sent is covered by the heading data rate that ranges from 0 to 6. 0 at the extreme and 6 nearby. Understanding this feature of LoRaWAN is quite sufficient. For completeness, I will overlay this graphic with the details used in the UK and European implementation of LoRaWAN, bitrate, and finally, receiver sensitivity. The gateway and each end device may be programmed to negotiate their optimum individual data rate based upon their local settings. This is called ADR, adaptive data rate. Everything is done within the end device to increase.
So we discussed a video about this spreading factor, and it makes LoRaWAN possible actually. So it's very, very important architecture. We see that it makes the RF performance of LoRa. So you see that there is a spreading factor we have mentioned here, 6, 7, 8, 9, 10, and 12. We see the SNR has been, degrading, but still subject factor 12, SF12, can even listen on an SNR of minus 20 dB. But here, what we have done, we have break the data in multiple of chips, thousands of chips. Whereas in spreading factor 6, we have only 64 chips. So this is the basic difference. By this, we take more time on air SF12. We'll have comparison in the next slide. Typical sensitivity also changes. If I take a consideration of our sensitivity, where we have inbuilt LNA is also available, which is provided in the LoRa chipset, we see that SF12 has a maximum receive sensitivity, where we can receive signal even on the minus 137 dBm of link budget, which is a big deal. You can't have this in FSK or double OK or maybe any of the IoT technology except Sigfox. So when we talk about SF6, it is still have a better receive sensitivity. Here you can receive data as good as Sigfox or kind of. LoRa has better RF performance in terms of receive sensitivity, in terms of SNR, even in terms of co-channel rejection, also improved to general RF interference. We see the time of the air in the next slide, how it impacts on time on the air also. So we see that on X we have payload size, and then the time on the Y side. We have indicated this is the top one is the SF12. You see SF12 take maximum time. If you want to send 50 byte of data, it will take almost 2 seconds of data. Whereas SF7, which is the lowest one operating here, will take very, very less time, 100 or 200 millisecond of time to send the same data. But on SF12, you can achieve longer ranges up to 15 kilometer. SF7 will still have a range of 3, 4, 5 kilometer in open space. Still, SF7 is far better than the other modulation technologies used in other RF technologies of LPWAN. This is the LoRaWAN basic stack. So you see the physical layer of LoRa. Physical LoRa is basically the chipset, gateways. You have different country band showing here. European band is showing there, US band showing there, India band is also there. Then there comes the modulation which we just discussed about. Then there comes the LoRaWAN MAC layer. MAC layer is the layer which communicates, which standardizes the communication with LoRaWAN network server. Here the classification of devices, the class A, B, C, and the options. They are the predefined architecture in LoRaWAN MAC layer, where you can decide the clock, you can decide the frequency, you can decide the region, you can decide all control where you need to configure a device. Then the top of them become the application space for sending us the data for a sensor. The payload comes in here. So this is typical LoRaWAN packet. So we will not discuss in detail. Just want to show you. So these are used in introducing the device to network, the preamble, and the header and CRC has been taken care. We have a payload which can go up to 50 byte in SF12, and it can go to 222 byte in SF7. So this is payload is variable payload. This is how the packet has been handled. You transmit the data on air. The time on air will depend on the SF you have used. Then you have SF and the payload. Then you have the receive cycle delay one. So when you send the data will travel to gateway, then travel over internet, then read to LoRa network server, and then the LoRa will send back the confirmation. Confirmation may be LoRa acknowledgement packet, or it may be some control packet. It will wait for some time, maybe a 2-second time. Then it will ready to listen the same frequency which is had to transmit it. It's called as RX1 frequency. So if you wait for another 1 second, or RX1 frequency. If data is not received in RX1 frequency, it will again wait for some time and go to RX2 frequencies. And then there will wait for RX2 frequencies for all together. Till the time you have a next transmit cycle. The classification of devices. So we see in the LoRa mats that there are three classes of devices. So why this classification is required? This classification has been required to maintain the power efficiency. You have a battery powered devices which will be sending data. You need not to communicate with the device. You just need to collect the sensor data. You should work on the battery powered devices in classification A. You can have water meter which is sending a reading every day. You need not to communicate with water meter other than the metering data. So you should go with class A. Then there's a beacons where you need some frequented data. You need every 1 hour data. You need you need to communicate with this sensor also. So this is a particular time interval. You decide on these beacons. So they work on the B class of devices. They are still battery powered devices, maintain still low power, but with the interval of listening mode available to them, you can reach the device. Like you want to send some command to class B devices. Sending a command to class A devices requires some more complexity. You can send to those devices also. But whenever they are sending data, you can't reach them devices other than when they are up for sending data. For class B, you can send some commands to these devices on some interval of time. So this is have some two-way communication available all the time. Class C devices are devices where connected with power sources. Here you can communicate anytime, available always for the RX windows. So you can send any command anytime, you can send data, you can so when you have some machine working in some industrial system, you need to always on availability. You need to go with class C devices. Another example is a energy meters, where you want to reach out the meters every time. What is the load availability? What is the power factor availability of this particular electrical line? You can use class C devices for that. So this is another classification of class C devices. We will not much discuss in here. We just tell you that it is just working on this window. After taking this window, they're only working for receive purpose. The beacon devices, when you talk about, is a beacon architecture. Whenever the beacon is available, you can reach these devices. Then there comes RX, the class C devices, where RX2 is continuous. You can reach anytime these devices. This is typical LoRaWAN gateway architecture, where we are using a LoRa PHY. LoRa PHY is nothing but LoRa hardware chipset. This is a baseband processor, 61301. Then we have a radio front ends. These front ends are, responsible for RF communication for DX-RX port. It connected with a gate, a LoRa antenna working on 50 ohm impedance. Then there comes to the gateway stack. Now, what is the gateway stack? Gateway stack is a whole library for LoRa bridge. It's what this LoRa packet forwarder connected with this. Packet forward changes the LoRa packet to IP packet. And the LoRa gateway code communicates with this PHY and sends the data to packet forwarder. Packet forwarder further sends this data to IP backhaul. This IP backhaul may be on 4G or maybe on Ethernet or something. And this works in a Linux ecosystem where you are using ARM Cortex A53. This is an example of gateway. So gateway works as a transparent device. Whatever data comes in, it sends to LoRa network server, or whatever coming from LoRa, it sends to device. Doesn't maintenance anything locally. Now we look at this server, LoRaWAN server. So this is the architecture which has been followed by LoRaWAN server. The gateway is connected over UDP. You can also connect it in some other protocol also. The LoRa basic station protocol also. We are talking about a basic LoRaWAN server, which has been used since long. But there is other architecture also, which works on LoRaWAN basic station architecture. You can reach the LoRaWAN basic station website for that. Here you can see an UDP communicating with the cloud server. This cloud server you can have an AWS or on a Google Cloud or maybe on your own premises server connecting with a public IP. You connect to the gateway bridge. Gateway bridge works with the broker, which is further connect. Or similarly, you same times you have LoRa network server, which is communicating with this broker. This LoRa network server has the communication happening. It has the LoRa MAC commands available with that. It has the basic RF command structure with them. The LoRa network server is further communicated with LoRa application server. LoRa application server is a registry of all the services where you can reach LoRa network server. Also, you can also reach any gateway. So they have the device registry, device activation, device registration, LoRa gateway registration, deregistration, change in the frequency, change in the ISM bands. So you can manage everything here. So you have the web interface available. You can connect with this on the integration. Many of the integrations are available. You can connect on these, and so the data can be sent over all these integrations very easily. You can have your own LoRa network server. It can be, it is available free of cost also, or also there are LoRa network server which is available on customized platforms. Both are available. So this is the process how activation takes place. So there are two procedures. One is OTA, where device has been activated over the air, and another is activation by personalization, which is device has been pre-registered before coming to network. ABP has been used because it is an easy process, but less secure. You enter the whatever the keys required during the manufacturing process, and devices are tied with a network ID. But in the OTA, you will not need to do all this. Whenever the device comes on the network, the LoRa network send. So it is more secure. So we have a trade-off just discussed on SF and the static factors. We again looking at this. So you can see that your red line is showing the time on air, and the black line showing the bit rate. So when you are in the vicinity of a gateway, you can have a bigger data rate. Now this data is automatically defined by LoRa network server. The LoRa network server which decides that which device works on which spread factor. So you must have the intelligence in your device to communicate with the server on different spread factors. We say that adaptive data rate shall work with your adaptive packet sizing also. This shows further about this. See, in the two gateways, gateway 1 and gateway 2, we have different sensors and devices connected with gateway 1. And this gateway 1 working with nearby devices on SF7, this gateway, and there are some SF9 devices which is connected with gateway 1. So if you connect with gateway 1, it will connect on SF9, but if you connect with gateway 2, it will connect on SF11. But the most remote area, you will work on SF11. Then comes the SF12. So this way, you can work on different device classes, different spread factor, and scaling the gateway architecture. Thousands of devices can be connected. Still, they are working in tandem with the. Now the frequency also comes in picture. You have 125 kilohertz of bandwidth available. You can create 8 channels. Then you have different spread factors, 6 spread factors. You multiply these frequencies with spread factors availability. You have 48 type of availability of frequencies. You can 48 devices can be communicate with one gateway. This is a very, very big channel availability in comparison to other IoT networks. Sigfox has very, very less in comparison to LoRaWAN in terms of channel availability. Wi-Fi does have a bigger channel availability, but not comparatively with LoRaWAN. License spectrum, LPWAN also have limited channel availability. Only the problem is that we have ISM band here. There are some people who does not work in the tandem with the specifications. So they create the problem. Otherwise, LoRaWAN can compete with the licensed spectrum users also. Just a minute, I'm muting the participants. We will see one more video from LoRa Alliance.
Issues with resources like water and energy, as well increasing awareness of safety, security and efficiency, are driving the need for more information and better options to connect and manage advanced sensors to build a smarter world. In a few years, global, national and regional networks will connect trillions of wireless devices. Even at home, hundreds of objects will be connected and send and receive hundreds of messages every day. You will be able to monitor and control any device that's connected to the internet. The Internet of Things is going to connect the world, and it will create lots of efficiencies and new business opportunities. Industry leaders initiated the LoRa Alliance, an open, non-profit association of members that understand that the Internet of Things era is now. Our mission is to standardize low-power wide area networks to enable the Internet of Things. The Alliance brings together companies of all sizes throughout the value chain who together build carrier-grade communication networks and sensing solutions to drive a connected world to its full potential. The Alliance members are actively collaborating to drive the global success of the LoRa Wide Area Network Protocol, also known as LoRaWAN. We continuously share knowledge and experiences to guarantee interoperability between LoRa network operators in one open global standard. To benefit from the global reach of LoRaWAN, sensors are being built based on LoRa chips and modules. Once your solution is ready for launch, the LoRa Alliance offers certification programs to ensure compliance and the ability to commercialize your offering around the world. Depending on the use case, your sensors can transmit messages and receive acknowledgements or responses by listening to the network after sending on fixed intervals or in an always-on mode to reduce latency. LoRaWAN is designed by the industry for the industry and provides the flexibility needed to cover almost any use case. LoRa offers unique wireless features that enable the connectivity of any kind of device or solution. LoRa is already a proven technology deployed in millions of sensors. LoRa is easy to install, extremely economical, flexible to adapt to many use cases, scalable to deal with growing demand, supports bidirectional messaging, and has embedded security and encryption to protect your data and privacy. It is rapidly becoming the carrier-grade low-power wide area network of choice of many carriers. Optimized power consumption results in a battery life of many years, enabling sensors and devices to send and receive information even when located indoor or underground. The opportunities and use cases are almost endless. Our LoRaWAN standard will make the Internet of Things available for everything and everybody. This open standard will be the key to success to connect the world. From monitoring industrial processes or machines, locating expensive assets, providing data to increase efficiency and make cities smarter through parking guidance, reduced energy bills for street lighting, or optimized waste collection, all the way to consumer solutions in smart homes or providing peace of mind for our loved ones. Together, we have the power to connect the community and build new business whilst ensuring a green and sustainable world for the generations to come. The standard is here. The innovations come from you. So get your company on board and join the LoRa Alliance.
We will discuss how the alliance is looking at. So, whoever is participating in this webinar should look at the LoRa Alliance standard, should be followed whatever you are buying or whatever you are working with or whatever you are intend to work with. So these are the LoRaWAN use cases you see. These are the LoRaWAN use cases. It is predominantly available in energy, water, gas, street light, parking, waste management, environment, healthcare, industrial, agriculture. So you will see lots of use cases coming day by day, with different kind of applications. So be ready for that and participate with us for that. We are manufacturer of LoRaWAN devices. We are already in all the ecosystem of LoRaWAN devices. Say module, gateway, or a LoRa network server. We work with many companies across India as well as abroad to look at the solutions they want. We also have these kind of modules devices with us, metering, gas meter, parking. We also have solutions, electricity, street light, irrigation. This is about us. We are a startup. We started 5 years back. Now leading LoRaWAN player of India. We have the team of electronics and telecom engineers working with us. And the motto is to bring disruption in IoT space of India, which has been predominantly taken over by other global players, so China and other European markets. So this is for the today. Tomorrow we will discuss on the hardware, the details of hardware of LoRaWAN in terms of gateway, in terms of end nodes, how they are categorized in terms of RF power, in terms of reception, in terms of communication with modulation, in terms of communication with their MCU, the stack, applications, and many more, even to the LoRa network server also. Now look at, you can reach to us on our social media handles. You can reach to our website, look at our products, our services. You can also reach out to us any query related to LoRaWAN. Thanks very much. Thanks all. Thanks, DocsPro team. It's over to you.
Yes.
I'll make.
Thank you, sir. Thank you for your time. I'm sure everyone has learned something new today. So this is it for today's session. See you all tomorrow.